doing this. So what are the biggest theoretical gaps in our efforts to use astrophysical sites to enhance our knowledge of neutrino physics and or element synthesis? So one obvious, I guess, answer to that is flavor transformation. I think it still counts as a theoretical gap because we don't know it nearly as well enough as we should. But yeah, what
can I add to that? That one thing I may have touched on this morning, but we didn't really talk a lot about is that even if your flavor transformation calculations are good, you still need to know the kind of input signal of fluxes and energy spectra coming out of the neutron star. So things like, and that's difficult to model because it depends on nuclear equation state, it depends on opacities. That is difficult, and so that's a little tricky.
Well, the other thing that George shortly mentioned, we do not really consider correlations between neutrinos in the supernova and mergers. So these many body effects may change certain consequences and may not. So it's one thing that is missing, and of course, we just started looking into those, but we are nowhere near a complete understanding of what may be needed.
I think maybe IceCube people would know better, but for me, it's also sources of the very high energy neutrinos, like it's still unknown. So we measure something, but we basically kind of don't know where it's coming from.
Okay, I can second on that. I think if we find the sources and understand the sources, that will give us the power to distinguish the different features in the spectrum. And the different features in the spectrum, basically finding the structure in the spectrum has a lot of implications in terms of how the acceleration is happening, how the neutrinos are produced, and also if you want to do cross-section measurements, flavor analysis, and stuff like that. I would add to that, since this is about like what we don't know, I want to go to the higher energy part. We don't have we don't have a very good understanding of the cross-section at very high energies. Without that, if we actually see a flux, we cannot tell what it is. We are expecting to see GZK neutrinos. No sources can produce ultra-high energy neutrinos beyond PeV or 10 PeVs. But if we actually see a flux, which is the scope of a lot of upcoming experiments, it is not clear what we are seeing. We just are seeing a flux because we don't know what the cross-section is.
Everything.
So I guess the other issue would be that, so suppose you have some astrophysical source and you are getting neutrinos from there and you are detecting them here. And so then there can be theoretical gaps in our understanding of the source, and then there can be theoretical gaps in our understanding of the detector. So that's the other side of the story. I mean, just maybe you can comment more on this, Alex. Just understanding of cross sections, or Arthur, if he's still here.
Well, I mean, these things are related in the following way. So let's say you have your understanding of what happens in the supernova, and it identifies some signal that you would like to look for. Whether or not things are observable depends on seemingly mundane things like understanding cross sections in the 20, 30, 40 MeV range. And it would be very good for our community to work on that. Like right now, there is one code, Marley, which was done by Stephen Gardner, who is absolutely great, but this was his PhD project. He was a student at UC Davis of Bob Svoboda, who was here early in the program. And he implemented some model, but he is the first person to say that this model is just zeroth order approximation to the problem. So how neutrinos of 30 MeV interact and what we will be able to disentangle from the signal in the detector, right, on argon 40, right. That's like the loop gets closed. Like we can predict interesting signatures where there are some, sharp spectral features or some moving features or some evolution of the spectrum. But if our resolution is A, poor, and B, misunderstood, then what can we actually see?
We don't really have a good theoretical basis at the moment for argon 40 neutrino interactions at that range. For the Gamow-Teller resonance, you can get some idea from charge exchange reactions. And for the isobaric analog states in argon, you can look at the decay of the beta decay of the mirror nucleus, and that's it.
That's it.
Once you go above about 35 MeV in argon, there is no experimental information to restrict your calculation.
And it's even lower than that. But so
It's probably
what
lower
Marley
than that.
does is they take input from these two things, and then above they have to resort to some QRPA theoretical calculation. There is this continuous step in between these things.
Theory calculations come with a lot of assumptions that should be checked against experimental information. That's why I'm talking about Gamow-Teller with the charge exchange and the beta decay with the isobaric analog state.
Right. So I want to go back to this, the first.
Can I just add to that, I mentioned this morning that the flip side of that is that same physics comes into play in stellar collapse, in electron capture. It's the same issue.
Yeah, same issue. Actually, of course, one thing I should add, that the biggest concern with the supernova observation is whether you can do flavor identification. And it's not clear to me at the moment that we can do flavor identification.
Yeah, well, for neutral current at Dune, for example, everybody says, well, Anna Hayes looked at it once, right? And that's the state of the art. So, I mean, I wish that there would be a more dedicated effort on that.
The branches, the gamma decay branches from excited states in argon 40 are measured. And what Anna pointed out is that there are two actually. There are two fairly energetic photons. And so a key question to ask the experimental community, the liquid argon detection community, is whether they can tag those high energy photons, whether they stand out in some way. We get this ball of photons, right, in the signal. And so if you can tag those and there's no electron in that signal, then you then tag the neutral current excitation in
what you have is several quantum blips, and then you have to go from there and reconstruct.
I have no idea.
So I want to maybe pose a question to the supernova community, I guess. In what scenario can we find ourselves experimentally in a supernova anomaly? What sort of signal do you not expect to see from a supernova? Because there's a lot of different features that you predict, but what sort of thing would baffle you, I guess?
I'll give you one, which I didn't talk about today. I guess I mentioned it, but just, if neutrinos have mass, you can change left to right or right to left. For Majorana neutrinos, that means changing neutrinos to antineutrinos. And everything about the supernova, including the nucleosynthesis, is sensitive to the mix of nus and nu bars. So the neutralization burst, which is when the shock comes through the neutrinosphere, should be mostly all electron neutrinos, 7 to 1 or 10 to 1, depending on whose simulation you look at. And so, yes, flavor transformation will modify that signal and change it into mu's or taus, but you don't expect a lot of antineutrinos there. So if you saw that, and you had the timing resolution to say that came from the neutralization burst, that would be unexpected and surprising.
Maybe our IceCube friends can comment on that. I thought IceCube could get good timing resolution, not optical, but
Yes, with new E-bars, you would expect to have a big burst in IceCube for a supernova up to, I think, LMC with a good significance. So, and the timing resolution can be as good as 10 nanoseconds.
Something also maybe kind of not expected would be if we see double burst, like one, the neutronization burst, and then the second one, which can be kind of associated with the quark-gluon phase transition. And that would be mostly also in nu bar.
I guess another unexpected scenario would be like if we know exactly how far away the supernova is and what the binding energy is. So from that you expect a certain number count or a certain flux of neutrinos, and you don't get as many. And the implication might be that some of them oscillated away to a sterile state or something like that.
So I have a question. If we have huge numbers of limits on new light particles coming from the cooling argument, what's the signal version of that? Can one ever determine new physics parameters from cooling arguments? Or is it just a limit setting tool?
I'm not sure if from the cooling argument we can place a bound. I mean, one example could be the heavy MEV neutrinos, but it's mostly, it wouldn't cool that much. It would be just mostly the decay that you see, and you can see the high energy part. I don't know if someone else wants to.
I guess one other maybe theoretical gap in, I mean, specifically to related to compact object environments is how well do we understand things like MHD turbulence, basically things that you can't do with spherical curves.
if you are referring to the second question,
No. I mean, this is probably still the first one. Like this is, does this count as lack of theoretical knowledge about using astrophysical sites to constrain neutrino physics or other BSM physics? Just not knowing about things like magnetohydrodynamic effects or turbulence or some large scale convective flows or something like that.
Yeah, I think the zoo of potential astrophysical phenomenon going on in the real supernova is kind of daunting. You know, I am no expert at all. I don't do these simulations. I'm more of a consumer of them. But there is seemingly a trend right now that the modelers can get the lighter progenitors to explode, and seemingly don't have nearly as much success getting the heavier ones to explode. And it's not known whether that's first of all, whether that's okay. And there's some, my understanding is there's some evidence from the observers that some of these things should explode. But does a high enough fraction explode? Don't know. Is there something missing in the simulations? Undoubtedly, there's something missing. But I'm a cynic. Is there some fundamental physics that maybe in the weak interaction sector or the neutrino sector that we're missing? I don't know how to answer that.
And I guess one other question that just came to mind, because I've sort of started crawling into this nucleosynthesis business only recently, and then the idea is that, let's say if you're trying to run a nucleosynthesis code with some outflow. Now that can either be some parameterized, analytic function, or it can be like a semi-analytic solution to a set of coupled differential equations, or it can be a trajectory of sophisticated 2D or 3D core collapse simulation. Now, if it is the latter, then the question is that like these simulations are computationally very expensive, very intensive. So you probably can't do hundreds of simulations to cover every possible base. So then if you take, say, one of them and you get some result, and it begs the question, like, how generalizable is that result? And I mean, if you are in a situation where you can't do hundreds or thousands of simulations to cover every single possibility, then what is the alternative?
Yeah, I want to just to follow up on something that you, George, just touched. So the list of physics, and if you like physics, supernova is a great place to work on, because there is just so much in various kinds. There is nuclear synthesis, there is a nuclear equation of states, there hydrodynamics, there's, as Amol mentioned, MHD, there are, fantastic things with flavor transformations, feedback between them, and so forth, right? So there are many things that, like 99 things to work on. And our community tends to like cluster and condense around a few and sort of get hung up on them. So I think it's perfectly fine that we all study fast collective because it's interesting, but we should not do this at the detriment of 98 other things that are not getting enough focus. And so I vote with my feet. I ended up doing nuclear synthesis these days precisely because I think there are many interesting questions that one can ask there. I don't know, like, how do we, as a community, how do we identify a broad list of interesting open physics questions? And if somebody wants to do neutrino transport, and as you say, that a lot of things depend on how neutrinos are transported out and how they decouple. We should tell, maybe students and postdocs who are picking topics that there are these things, they're all on the table and they're very interesting. Like, it would be good for us to explore more. Like, I think that even, studying turbulence or studying MHD things and so forth is quite interesting and may lead to new signatures that we have not seen in neutrinos. Another topic I'd like is if there was eventually some way to connect observable neutrino signatures and nuclear synthesis, that would really be, very cool. If you could look at the signal and say this supernova had good conditions for nu-P, that would be cool. Great.
Anyone has any other comments about the first point? Should we move to the second one?
Can talk about sources for IceCube ad nauseum, right? Because this is such a cool topic.
Well, on the second point, I want to remind people, perhaps not considered as such, but to me, one of the holy grails of cosmological neutrinos is to measure them. Neutrinos left over from the early universe, okay? It's not going to be easy. There are attempts to do that already, and it probably will require very fresh thinking in neutrino detection at very low energies. But there's one thing that one can do on the way there, and that is trying to detect the thermal neutrinos from the sun. Thermal neutrinos from the sun come with the energies with the temperature of the sun. So their energies are keV as opposed to cosmic background energies. So in principle, they should be amenable to detection. even like the very low energy end of the PP neutrinos in the sun, for example. This is something I hope that the experimentalists are thinking about, and eventually they will be able to do something about this. But to me, these are like obvious, especially the thermal neutrinos from the sun are low-hanging fruits at some level.
Very high hanging for experimentalists.
Yes, but you have to be.
To your point on the relic
It,
neutrinos,
it took many years to detect PP neutrinos, so it was. So I agree with you. I would like to. I would love to see them. But
Younger, a typical neutrino experiment measured zero. Every single neutrino experiment measures zero. Now that's not the case. So we actually have come a long way. And why do we stop here? We have to be more ambitious.
so can I address your point about relic neutrinos from the early universe? I agree. I will point out, however, that there are indirect measurements of them, and those are the light element abundances and effective. And coming up soon, some kind of constraint on what the cosmologists call sum m nu, the so-called sum of the light neutrino masses, which is actually not the sum of the light neutrino masses. It's actually a measurement of the collisionless damping scale of the relic neutrinos. So that encodes information on the spectrum. The light element abundances encode also information on the spectra and the histories of those neutrinos. So, and they're going to be measured with higher precision in stage 4 CMB, and we'll have, according to the astronomers, 1% precision or better than 1% precision in the primordial deuterium abundance. So if I put those two things, those four quantities together, maybe something shows up. And Kev, you thought about this too. So.
Well, I think we're going to get to the point where the question on the sum of M nu is going to be a much more complicated question, which is how does hierarchy and the thermality or lack thereof of the neutrinos fold into what we call sum of M nu, or what cosmologists call that. So getting, disentangling all of the things that actually affect how neutrinos affect cosmology in the CMB and large scale structure is going to get a lot more interesting as we get to the super high precision era, like sub percent, sub 10th percent possibilities. Yeah.
I'll add something on the more of the all the way to the other side of the energy spectrum. There is a scenario in which the new physics exists at the, let's say, 100 TeV scale, and instead of the 1 or 10 TeV scale. And in that case, we would have to turn to neutrino sources that are producing EeV scale neutrinos, because that's when you get center of mass energies when they interact of order 100 TeV. And so there could be a scenario where the only let's say, avenue we have to find the new physics would be to understand better how these sources emit such neutrinos and then detect them, because then we'd be able to test, heavy neutrinos and all sorts of new physics at the high energy scale.
I mean, I think DSNB would be helpful too, to observe it finally. We could learn something maybe about how hot is it, and that could give us some information either about neutrinos emitted from average supernova, or if we also start observing basically kind of turning off stars, maybe it could also give us some information about black hole forming supernovae.
Your time.
Yeah, since this is some futuristic discussion, so we can now start to consider maybe there's space detector that we can use to study some kind of either neutrino or related to neutrino signature, like some Ars-Carrier signature or things like that. I don't know how realistic that is, but NASA has a lot of funding and they want to put a lot of detectors in space. So that's a kind of parallel thinking that I think is futuristic and not a lot of people explore, but there's something we can think more about, like the space detector of muon or other stuff. Yeah, thanks.
Well, I know that George wants to turn Europa into a neutrino detector. I know that you want to turn Europa, the moon of Saturn, into a neutrino detector.
You know, put some kind of herbicide under the ice to kill whatever's living there, and then turn the whole thing, put, you know, photosensors in there and turn the whole thing into a giant version of IceCube. I don't think that'll go over very well. Yeah.
Although,
but as Kev talked about yesterday, I mean, it's remarkable to me and you that actually the most stringent limits on this sector of sterile neutrino properties, KeV scale, mass scale, comes from X-ray astronomy.
Maybe I could just ask, what's the useful thing that you would learn if you measure thermal and solar neutrino? Because the temperature we know well. So.
Well, the temperature is not is not known as accurately as some time ago. John Bacall had the idea of measuring the beryllium-7 line width, and from that he would get the temperature is not as well known. Well, first of all, you would confirm that there are thermal neutrinos. I think it's good astrophysics, good solar physics, and it contributes to the main sequence theory of main sequence stars. You may not learn much about neutrinos, but you'll learn how to detect really low energy neutrinos.
Could that also help us to like make sure that number density of electrons is what it is and there is no other weird potential?
It would also be another test of KUV scale, sterile neutrinos. If there's something there, we would see a feature in that spectrum, right?
You would need a lot of statistics for that, though, right? Would you get such good statistics from thermal KV neutrinos in the sun?
Can anyone do this beryllium-7?
Not that I know.
Yeah.
You know, it's too close to the surface. Maybe,
That's I'm actually going to go back to the first question because I didn't get a chance to ask it. What's going on? What's the status of our process nucleosynthesis? Everybody kind of talked about it a little bit, but I still don't get a really good feel.
Good.
So what exactly do you mean? What is the status? You mean where does it come from? So I think the observational information is there's the kilonova signal that suggests that you get lanthanides from the kilonova. So that's part of an R process. So some neutron star mergers make part of an R process. Okay. And then there's metal poor stars in the galaxy. And in those stars, you often see the rare earths together with the third peak. So the lanthanides show up with gold and platinum. I don't know if they see gold, but they see platinum. Okay, but not always. Sometimes the pattern goes along and then it kind of dribbles off. And then another piece of evidence is in ultra-faint dwarfs in old galaxies. And if you look at ultra-faint dwarfs, mostly you don't see our process elements, but you know, like in reticulum 2, you see some R process elements. So that's 1 in 10. So that favors a rare event. And then of course you have the solar system data. So it's all more or less consistent with neutron star mergers, but it's not. You haven't shown that it's neutron star mergers. And when you make models of galactic chemical evolution, with what we know about neutron star mergers, it becomes a little difficult to reconcile everything. And so there's a lot of debate now does it all come from neutron star mergers, or maybe some of it comes from somewhere else? So most people do not favor core collapse, your typical core collapse supernova making our process for both observational and theoretical reasons, but more rare supernovae, for example, collapsar scenarios, jet-driven supernovae, or just any rare supernovae that you don't necessarily know what it is, but it might operate earlier in the evolution of the universe, and neutron star mergers are a subject of discussion. So you could certainly have multiple R process sites.
Thanks. But for type 2s, the electron fraction gets low enough or not? Or?
So the theoretically, or the models of core collapse supernovae generally don't go out all the way unless they're one-dimensional. And those one-dimensional models go through a stage where they make some R process, say, out to the second peak or so, but not a lot, and it depends very much on the model.
I just add to that yeah, I mean, there are simple nuclear physics issues also. The thing that Brad Meyer and I call the alpha effect, for example. It's just a generic disease that happens in relatively high entropy outflows when you have, you know, a substantial nu efflux and a nu bar flux. I'll add to Gail's laundry list, though. There might be things that are not supernovae. I mean, Udai is in the audience, so Udai and I kind of represent the lunatic fringe of ways to get neutron stars to implode, either by eating the wrong kind of dark matter or primordial black holes, for example, something like that. You might get our process out of that. And that would be a uniquely taggable event. Correct me if I'm wrong, Udai, because you wouldn't expect any gravitational radiation from that, unlike a binary neutron star in spiral. And likely not get much of a neutrino burst either.
Yeah, thanks, George. So I completely agree that's an interesting signature to look for. And DS potentially do have the data already to search for this faint kilonova kind of event without gravitational wave, but nobody really studied it yet. And it probably, yeah, it's fainter, so you have to actually have some specific search for this kind of event. And also, I think the simulation also, it depends on different model you put in, but some claim is the ejecta is very small, so there's not a lot of emission, but some, like your estimation could be larger. So I think there are larger uncertainty there. But anyway, if you see a kilonova type event without gravitational wave, it's always interesting, and then we can debate what that is. But yeah. Thanks.
Okay, so one more question related to the second point. Neutrinoless double beta decay. I mean, if we were to see it, we would, of course, learn that neutrinos are Majorana, but what else can we learn from it? And where else can that be useful? So open question to panelists and audience. Because
Yeah, so that would be the case for sure, right? That you would generate Majorana neutrinos at some level, but yeah, you can perceive that process as a probe of new physics in general, because it doesn't have to be actually the light neutrino exchange mechanism, which is the dominant contribution.
right.
It can be any other delta L equals 2 Smith operator, right? So yeah, dimension 7, and it has been shown that actually there are even models in which these contributions can be the dominant ones. So yeah, it could be all kinds of.
How much power do the current measurements have to break that degeneracy, like to pinpoint what exactly is causing it, or
Yeah.
or what other complementary measurements would we need to break that degeneracy?
Yeah, that's a good question. So that's not so easy, of course. But exactly for that reason, it makes sense to build like several experiments with using different isotopes.
Right.
Because yeah, that would be potentially way how to disentangle something. Another way, so if you observe the process, right, then it would be totally worthwhile to track also the outgoing electrons, right, and so the energy spectra, and also the angular correlation of the electrons actually could tell you that there is another contribution, for instance, because yeah, that would be potentially affected. But yeah, but it would be hard, and you need also like potentially maybe even in colliders you could search for lepton number violation, because when you look at these higher dimensional operators, that they would correspond to new physics at even like TV scale, right? That's the dimension 9 operators, the current limits on the half-life. If they were responsible for neutrinos double beta decay, then the new physics would be somewhere around a few TV. So yeah, we should see somewhere there.
So anything else related to point number 2? Or
can I just say that this not observation but experiment? I mean, many of the astrophysical issues we discussed today become more definitive, more meaningful if we know what the hierarchy is. So many things in cosmology, the issues associated with Big Bang nucleosynthesis and weak decoupling, and also things we talked about flavor transformation and supernovae. So it would really help to know the hierarchy, and I know that's a key objective.
So any comments about point number 2, or should we move to point number 3? Is it somewhat degenerate with point number 1, or did you mean something else by it? Are we neglecting key areas?
I just said that there are so many interesting things to work on, and we should be more, more fermions if you want, right? There are 99 things, and we should try to occupy as many of them as we can. As far as neglected area, one thing that I want to touch on is the communication between our community and supernova modelers on one side, then experimentalists on the other side. For experimentalists, they need some kind of clear examples of what features they should go after. So You may not care about your energy resolution at Dune so much if you don't have features in your spectrum that require good energy resolution. And so I think we should communicate to them examples of interesting signatures so that they can be used as templates when they, benchmark their various, experiments. And maybe that will encourage this program of measuring cross sections at pion sources and so forth. And for modelers, they do these super hard calculations and they die at 1 second, right? Because getting the explosion is the goal in and of itself. But then it turns out if you want to do nucleosynthesis, then such a calculation is not good for you because you need to know what happens after that. And if you want to model the neutrino signal, then you definitely want your simulation to run until late times. So there should be a closer feedback loop to modelers also from our community, what we would like them to do. I mean, running a long simulation is expensive in terms of time and so forth, and they need a good reason to do it.
The modeling community actually has been reluctant to pay attention to us.
Right.
Flavor transformation, neutrino physics community. If for no other reason, because the physics is really complicated, and these codes are already pushing the limit of what we can do, computationally. So, but they're paying attention now. So they're now trying to integrate at least some flavor physics into these simulations. So, and it's difficult.
Well, the people who are my age and maybe older will recall that neutral currents were not in supernova codes until late 1970s, early 1980s. The reluctance goes way back. It's not new. Well, one thing I would like to see, it's not necessarily progress in the near future. It's not only effective for astrophysical neutrinos, but all of neutrino program. I would like to see more measurements of neutrino cross sections so that we can actually improve generators, which of course will certainly be very helpful to high energy experimental program, but it also will be very helpful to astrophysical neutrino program. That's what I really would like to see.
How are we doing with time?
How much time did we have? Was it 45?
Yeah, so we can declare a victory anytime people feel like it.
Yeah, unless someone has a specific comment on point number 4.
Yeah,
maybe the
that's a good
people
one.
who wrote snow mass white papers know more about this.
People have
in the near future.
some gut feeling about which fields are going to develop. I mean, predictions are difficult, right? Especially about the future, but still.
I'll say something very quickly. I think the experiments that are turning on, looking for precision measurements of large-scale structure and the CMB and essentially cosmological experiments are the most promising in the next, let's say, 5 years, because we are really approaching the point where we're starting to test lambda CDM. And that's where it seems like we could get some clues as to where to look next, because it seems like we are sort of looking everywhere for something to grab onto, and that may give us something to aim for.
Any other comments from the audience, from the panel?
I thought you would say atmospheric neutrinos at IceCube.
If the K-internet commissioning completes and they start seeing atmospheric neutrinos, then we would have additional degree of power to do oscillation studies with these detectors. This is going to be very helpful with regard to the atmospheric neutrinos. The other thing is that the growing statistics between these, let's say 10 TeV to 1 PeV or 10 PeV is going to be fruitful in terms of identifying at least some structure in terms of anisotropy. And that can venture in a lot of different studies, either astrophysical or like PSM scenarios. So I would expect that to appear at some point in the near future, not very long future. I think that people have put a lot of hope in terms of very high energy part of the spectrum into the future experiments, next generation, either IceCube Gen 2 or the radio arrays. But I think this energy range is going to be very important and very useful for future studies. And in terms of what we are neglecting, I just go one point back here. So we have talked a lot about the high energy end of the spectrum, but we really don't know what is going on at the other end of the spectrum because we are overwhelmed by the background. But it doesn't mean that there is nothing there. We know that, for instance, when it comes to the oscillation, tau appearance becomes very important there, right? And I think that happens, and on the other end, because of the larger statistics, is going to be very useful. I think we could have invested more into that, like 1 TeV to, let's say, 30 TeV or at most 60 TeV region. And I think it is a place to look more into.
Since we're talking about IceCube, so one can ask about what happens to the prediction for the GRB neutrinos, right? That's an interesting topic. And the reason why I ask is, so let's say there is a spectrum from GRBs, but it's not at 10 to the 15. It is, let's say, just below 10 to the 14. Can I go after it if I look at your data and try to do coincidence studies? Right? So normally it's buried under atmospheric background. But if I try to correlate with GRBs, then maybe I can look to see if something is there. I mean, have you guys been doing these types of studies, and what's the outcome?
So you're talking about usual GRBs.
Usual GRBs, which were the Fireball model, used to be sort of the stand-in, the base go-to model for IceCube, right?
Yes, but
and then it turned out to not be there at the level that those models predicted. But maybe we can find those neutrinos somewhere.
Well, yes, and the analysis has been done. It didn't discontinue, and you actually have a good sensitivity because of the time, right? So you are not actually overwhelmed by the background when you are looking at the short time scale with regard to the GRBs. You actually can look for them, but the coincidence has been not seen so far, right? And we actually the new analysis, so this is the part that I cannot complain about the negligence, because the sample that was actually used for the oscillation studies, so which goes to very low energies for IceCube, has been used to look for GRB, which is, I think, a very important thing that happened. And there are models that actually predict very low energy, in terms of IceCube, very low energy neutrinos from GRBs. And this is going to continue. Whether or not it's going to find something is another question. But yes.
I mean, it's very cool, right?
Yes.
That flux is missing, right? And even if you say you looked at lower energies, and it's not there either in terms of coincidence studies.
It is not.
That's an interesting implication, don't you think? Or
I do think that it is. As you mentioned, GRBs were one of the main motivations here, right? They are very powerful, they're very luminous, and a lot of interesting things are related to them. The thing is that we have not found any coincidence, but depending on who you ask, it might not be very surprising, depending on who you ask. The other thing is that we are doing we're doing this not not with full information. Let me put it this way, right? The spectral features that we do this in analysis is very simplistic. We just assume a power law. The flux is not a power law. We know that, right? Our inability to incorporate or to have the model-dependent scenario where the flux is actually featureful is something that is not helping with these searches, any of these sources, including GRBs. There's also other factors that different models predict, or different time scales predict different scenarios here, and we are not sensitive to some of them, right? So the time might help with this, and yeah, that's.
It's a very interesting topic. So
yeah, it
maybe
is.
we shouldn't, take this discussion too far in that direction. But it is the physics of astrophysical sources in general, what they are, and we can, if after 10 years we can already make some, solid conclusions. It's just a very cool thing about IceCube. I'm just thinking in terms of time, we can
transition
try
to
to
panel.
make an adiabatic transition to the next panel, and thank all the panelists here.